Hey guys, welcome back to our video series covering custom automotive tech development. We're currently covering hardware and making our way through the various options and setups to get your custom project off the ground. Today, we're getting hands-on with MCUs and MPUs for your custom automotive projects as a maker. We'll start by breaking down the differences between them, then tackle the real-world complexities of integrating one into your own design, focusing on necessary peripherals and why choosing the right chip from the get-go matters. Let's get the acronym TRAIN going and get into it. Oh, and if you are new here, don't forget to like and subscribe. Let's start by taking a look at what MCUs and MPUs are. The differences between these chips have evolved over time and can sometimes blur with modern high-end devices. But generally, MCUs are optimized for simple, efficient tasks, while MPUs handle more complex, general-purpose processing. In the real world, some of the differences that will affect your project are memory, with MPUs often requiring external memory, power consumption, where MPUs generally use significantly more, and performance. While some MCUs have made large advances in the last decades, MPUs are generally orders of magnitude faster. Now, integrating an MCU or MPU into your own design isn't plug and play. There are some complexities to navigate, especially as a maker building from scratch. Let's take a look at power options, as getting the supply right is foundational. Is that a word? Foundational? Let's just assume it is. Powering your chip involves choosing between regulators like buck converters, LDOs, or stepping up to a PMIC. Lots of acronyms here. So, a buck converter is a switching regulator that steps down higher input voltages efficiently, making it ideal if your power source is variable, like a car battery. It saves energy, but can introduce some noise. An LDO, or low dropout regulator, is a linear device that's simpler and provides clean, low noise output, perfect for sensitive analog parts. But it's less efficient and generates more heat when dropping voltage a lot. There's also a limit on how much of a drop in voltage an LDO can provide, so check the datasheet closely. For more complex setups, a PMIC, or Power Management IC, combines multiple regulators, like bucks and LDOs, into one chip to handle various voltage rails for your MCU or MPU and peripherals. It's great for minimizing board space and simplifying design, but it adds cost and requires careful configuration. As a maker, start simple with an LDO for prototypes, then optimize with a buck or PMIC as your project grows. Keep in mind that a PMIC may come programmed from the factory for specific voltages, or it may require a custom hardware setup or evaluation board to program the chip before integrating it into your design. Beyond power, integration challenges include laying out your PCB to manage noise and heat. Poor routing can cause signal interference or overheating. Picking the correct MCU or MPU from the start is essential, so make sure you factor in your project's needs like processing speed, memory, and I/O pins to avoid redesigns later. Speaking of memory, let's break down the different types of built-in memory on MCUs. TCM, DDR, and flash, and what they're good for. TCM, or tightly coupled memory, is a type of fast SRAM with zero wait states and the lowest latency, directly coupled to the CPU for critical code and data. It's perfect for real-time tasks like interrupt handlers or performance-critical algorithms. Choose higher volumes of TCM when your project demands ultra-low latency and high-speed access to keep operations smooth. DDR offers high bandwidth volatile memory for handling large datasets quickly. While often external, integrated DDR in advanced MCUs is a huge advantage, aiding with video transmission by buffering frames or supporting graphics-intensive apps. Opt for higher DDR capacities if you're working on multimedia, data processing, or anything needing substantial temporary storage. Flash memory is non-volatile, ideal for storing code, bootloaders, and persistent data that survives power cycles. It supports execute in place, XIP, for running code directly and can store splash screens, data logs, or even video clips. Go for larger flash when your projects involve bigger firmware, extensive logging, or media storage to avoid running out of space. Now let's take a few seconds and discuss ARM Cortex cores, which many MCUs and MPUs are based on. So let's clarify the main types. A, R, and M, listed in order of performance, from most performant to least performant. Let's start with Cortex-A cores, which target high-performance applications, running complex operating systems, and handling multitasking, like in infotainment systems. Integrating an A core into a custom design is harder than an M or R core because it often requires managing many different voltage levels and precise startup sequencing to prevent damage and ensure stability. A PMIC is essential for smooth Cortex-A core operations. Next, Cortex-M cores are designed for microcontrollers, focusing on low power and real-time control in embedded systems, like sensor processing in your automotive builds. They're efficient and cost-effective for simple tasks. And finally, Cortex-R cores are for real-time, high-reliability scenarios, often in automotive environments where safety and fast response times matter. Performance-wise, these generally land between A and M cores, but lean more towards M cores than A cores. Make sure you have an understanding of the differences between these chips, at least on performance levels and complexity, before moving on with your project. Once you've selected your core, consider operating system options like Linux or RTOS. Linux is a full-featured operating system great for Cortex-A cores, handling multitasking, networking, and user interfaces in more advanced setups. We advise against using Linux in anything real-time related where MCUs excel. It introduces complexities that are not necessary if an MCU has the required performance level to get the job done. RTOS, or real-time operating system, is lighter and designed for predictable timing as well as multitasking. It's essential to run RTOS on projects that require maintaining real-time capabilities and ensuring tasks execute without delays. RTOS also helps with power efficiency, as it optimizes sleep modes and resource use to extend battery life in your projects. Realistically, expect to run RTOS on M and R cores for their embedded, real-time focus, but not typically on A cores, which lean toward general-purpose OS like Linux. However, while not typical, some MPUs like the Renesas RZ series provide RTOS options on A cores, which, combined with built-in RAM, is amazing for efficient, high-performance embedded applications. As usual, before picking an MCU, always check the available software stacks and documentation. Make sure comprehensive examples, libraries, and guides are there to support your build. You'll want to focus on your project without having to reinvent the wheel. We'll cover OS options and multi-core systems in more depth in another video. To help you choose the right MCU, let's look at options from big players like NXP, STMicroelectronics, Renesas, Infineon, and Texas Instruments, focusing on their Cortex cores and performance. Starting with NXP, their S32K5 family uses Cortex-M cores running up to 800 MHz, offering high efficiency on 16 nanometers process for demanding tasks. The IMX-RT1170 features a Cortex-M7 at 1 GHz for top-tier real-time processing, and a Cortex-M4 at 400 MHz for balanced workloads. STMicroelectronics Stellar series employs Cortex-R52 multi-cores for high-performance automotive control, while the STM32H5 uses Cortex-M33 for secure, affordable options up to certain speeds. Their STM32N6 boasts a Cortex-M55 delivering 3360 CoreMark scores. Renesas's RA8P1 sets a benchmark with a 1 GHz Cortex-M85 and 250 MHz Cortex-M33, excelling in AI-accelerated tasks at up to 256 GOPs. The RA8D1, RA8T1 offers 480 MHz performance for versatile applications. Infineon's PSoC control MCUs feature Cortex M33 up to 180 MHz for efficient motor control, and PSoC Edge includes Cortex M55 for ML enhanced sensing. Texas Instruments MSP M0 series uses Cortex M0 Plus at up to 80 MHz for compact, low-power designs, scaling to higher performance in their ARM-based lineup. These options give you a range from entry-level to high-end, matching your project's needs. So, lots to choose from at every performance level. Let's take a look at a common pitfall that we feel is not thoroughly explained when reading the marketing materials for these products. While many CPUs offer a mix of A cores and M cores, getting them to work together can prove difficult or even close to impossible due to missing drivers, documentation, or other specialized software. The basic idea behind these multi-core setups is that you would run Linux on the A cores and RTOS or bare metal on the M cores, giving you the best of both worlds, a fully fledged OS and real-time operations. Our advice is to take a close look at the documentation if you decide to go with a multi-core setup. Ensure there are extensive working examples and implementation instructions to support intra-core communication like RPMSG on the exact hardware platform you are targeting. There you have it, a starting foundation on MCUs and some of their integration hurdles, Cortex cores, basic OS insights, and key MCU options to consider in your custom automotive designs. Remember, start with the right chip and power setup to keep things smooth. Also, keep in mind that this is a top-level overview of challenges and options. Every topic we covered today has the capability to turn into its own full-fledged project, like integrating DDR memory and actually getting it to work. That's why it's important to go for the best chip available that already incorporates as many features as possible to accelerate your development time. That's it for today. See you in the next one, where we will cover popular SOMs and their quirks and features. Like, share, and subscribe for more maker tips.